Welcome to Trust the Process. In this video, we'll be talking about tutorial sheet 2, question 2. So question 2 reads, a horizontal block spring system with a block on a frictionless surface has a total mechanical energy of 47.0 joules and a maximum displacement from equilibrium of 0.240 meters. So just what the question is saying in form of a sketch. We have the block spring system, that is the block spring system. So when the spring is undisturbed, that is what we have, and then it is going to be stretched to that amount. So this is going to be x, which is equal to 0.24. okay, that is the maximum displacement. So this can also be equal to a, because we are saying it is the maximum displacement, and the maximum displacement is nothing but the amplitude. Alright, so the first question is saying, what is the spring constant? So with reference to the first question of this tutorial sheet, we are saying that there are three equations that can be used to find the mechanical energy or the total energy of the block spring system. And one of those equations, we said it can be given by E being equal to 1 over 2 Ka squared. And according to the data, so far what we've been given, we know that we have the total energy E, which is 47 joules. Okay, and then we also have amplitude, which is 0.24 meters. What else do we have? This is the information that we've been given. So according to this information, how can we find the spring constant? So using this equation, we've been given the total energy. We also know the amplitude. So it is just a matter of making this one subject to the formula. We can cross multiply or multiply the entire equation by 2. We are going to have 2e is equal to Ka squared. Then K will be given by 2e over a squared, of which we know that this is nothing but 2 multiplied by the energy given, which is 47, then divided by the amplitude that we have is 0.24, which has to be squared. So when you punch in that, you are going to have your answer in Newton per meter. That is our spring constant. Alright, so part B of the question is saying, what is the kinetic energy of the system at the equilibrium point? What is the kinetic energy of the system at the equilibrium point? So at the equilibrium point, we know that x is equal to 0. And at this point, using this equation, using equation 1, which is E is equal to 1 over 2 mv squared plus 1 over 2 kx squared. When x is equal to 0, this guy becomes 0. And the total energy only becomes equal to the maximum kinetic energy. That is what we have. So what we can say here is the kinetic energy at the equilibrium point is just going to be equal to the total energy of the spring, of which we say the kinetic energy will just be equal to 47.0 joules. That is what we are going to have, 47.0 joules. Alright, so part B is 47.0 joules. Then part C is saying, if the maximum speed of the block is 3.45 meters per second, what is its mass? If the maximum speed is 3.5 meters per second, what is its mass? So the speed here, they are saying that the maximum speed, Vmax, is equal to 3.45. And we know that the total kinetic energy is given by 1 over 2 m Vmax squared. And we have the kinetic energy, which is 47. The mass of this block is what we are looking for. the Vmax has been given. So just making the mass subject, you say multiplying by 2 then divide by Vmax. Our mass will be given by the total kinetic energy, which is also equal to the total energy multiplied by 2, then so this is multiplied by 2 then divided by Vmax squared. This is 47 and then this is 3.45. So you say the mass is going to be 2 multiplied by 47 divided by 3.45 squared, and since it's a mass, it's going to be in kgs. That is how you find part C. Part D is saying what is the speed of the block when its displacement is 0.160. What is the speed when its displacement is 0.160? So now the value of x is 0.160. That's what they are saying, and we can use the first equation, which is E is equal to 1 over 2 mv squared plus 1 over 2 kx squared. So we're looking for the speed. This is the speed. We know that this is 47. That is 47, we know, and the mass has been found from the previous question. What we are looking for is this speed. The k is also known, the x has also been given. So it is just a matter of making this one the subject of the formula and plug in the values. So making this one subject, you say you have 2e is equal to mv squared plus kx squared. Then this term can go the other side, then you divide by m. So you're going to have v squared is equal to 2e minus kx squared over m, and then the v is going to be plus or minus the root of 2e minus kx squared over m, or all of them under the root. So the total energy is 47. The spring constant has already been found from the first question. The value of x here has been given to be 0.16, and the mass has been found from the previous question. Hence, this is going to be the velocity or the speed at 0.160 meters. Alright, question E is saying find the kinetic energy of the block at 0.160 meters. Find the kinetic energy at this same point. So now, we know the velocity at this point is given by this. This is the velocity at 0.16 meters. How can you find the kinetic energy? Kinetic energy is simply given by 1 over 2, the mass multiplied by velocity squared. So here, the mass is what you found in that part. Then the velocity, you are going to use the velocity at this same given point, of which this is the velocity they are talking about. So after punching in the value for velocity, you use it in this formula to find the kinetic energy at 0.160 meters. That is how you do it. Alright, let's go to part F. Part F is saying find the potential energy stored in the spring when x is equal to 0.160 meters. Find the potential energy stored in the spring when x is equal to 0.16. So we know that the energy stored in the spring, the potential energy is given by 1 over 2 kx squared. We already know the value for k, and they are saying that the value of x is 0.16. So this shouldn't be a big deal. The value of k is what we have in part A. Then the value of x is that. Just plug in the values and punch. This has to be in joules. Same applies to the kinetic energy. They have to be in joules. Those are the SI units for energy. Okay, what does the last part say? The last part is saying, suppose the same system is released from rest at x is equal to 0.240 meters on a rough surface so that it loses 14.0 joules by the time it reaches its first turning point. This is supposed to be first turning point. after passing the equilibrium. So here they are saying that this block is now resting on a rough surface, meaning there's going to be friction, and that friction is what is going to cause the system to lose some energy over 14 joules according to the equation. So they are saying that this system was starting from this point after being stretched, so it is going to lose the energy of 14.0 joules by the time it will reach its first turning point. And in the brackets they are saying this turning point is after the equilibrium, which is x is equal to 0. So if this is the point x is equal to 0 there, if this is the point that we have, which is x is equal to 0, we can say the turning point will be somewhere here. But remember, this object is coming from x is equal to 0.4. That is where it is going to be released from. Now, if this surface is smooth, we're expecting this object to go back to negative 0.24 if it is a smooth surface. But this time, they are saying that the surface is rough, hence some energy will be lost due to heat. Now, that energy which will be lost will cause this block not to go back to negative 0.24, because if the maximum displacement is 0.24, the minimum displacement has to be negative 0.24. So if there is going to be some loss of energy, meaning it won't be able to return to negative 0.24. But according to the equation, they are saying that it is going to turn from a point that is after the equilibrium. So we are expecting the turning point to be after this line here. So it has to be somewhere here. So if this is x is equal to 0, then that is positive 0.24, then it has to be a negative value. The point where it is turning from has to be a negative value. But what do we know about that point? What we know about that point is, the time it is reaching that point, it is going to lose 14 joules of its energy. And we know that the total energy is 47, then losing 14, it will mean it will remain with 33 joules. So at that point where it will turn from, it is going to have the total energy of 33 joules. And again, we know that at the turning point, the velocity is equal to 0. Now, if the velocity is equal to 0, how can we find the position at that instant? Where will that block turn from? So what we are saying is, from equation 1, we have E is equal to 1 over 2 kx squared plus 1 over 2 mv squared. That is equation 1. But we are saying that at that turning point, at that instant where the block is going to turn from, the energy is 33 joules. Then we have 1 over 2. The value for k is known from the first part. X is the position, and that is what we are looking for. And then at the turning point, velocity becomes 0. At the verge of turning, velocity is equal to 0. So this guy vanishes. So making x subject of the formula, you multiply throughout by 2 and divide by k. So our x squared is equal to 66 divided by k. Then you square root both sides. You are going to have x being equal to the root of 66 divided by k. Now, this can be positive or negative. Which value are you going to get? And it will be meters. So according to what the question is saying, it was starting from 0.24. And by the time it is reaching its first turning point, which is going to be after the equilibrium. So if they say after the equilibrium point, then the turning point is going to exceed this line, meaning it will be on the negative side. And for that, we are going to choose a negative value as our answer. This is going to be the instant at which that block will turn from. Alright, hopefully this is clear, and this marks the end of question 2 of tutorial sheet 2. Thank you so much.